Welcome to Saitechinfo channel, my dear students. In this tutorial, we will be discussing about the thermodynamic principles of metallurgy, where we will be explaining more about the Ellingham diagram. Harold Ellingham used the following relations to calculate the delta G value. Delta G naught at standard state at various temperatures for the reduction of metal oxide by treating the reduction as an equilibrium process. So he had this assumption, that is the metal oxide formation or the reduction is in equilibrium process. So that was his first assumption. And based on that, he plotted a graph that is, he put the temperature in the x-axis in Kelvin, and in the y-axis he put delta G value, not you can put at standard state. So he was able to get, by that is plotting this curve with various metal oxides, he was able to get certain graph that is with positive slope like this, and certain graph, for certain metal oxides he was able to get the negative one, and in certain cases he got, that is, the straight line with the slope 0. So in this case the slope is, that is, positive, whereas in this case the slope is negative, whereas here the slope is 0. So likewise he was able to get, that is, as a first case, this is case number 1 where the slope was 0, and in certain cases he found the slope was negative, so we can put 2. This is negative where m minus m, so the slope is negative, and the slope is positive in the third case. Okay, now let us analyze all these three, and based on these expressions only he was able to get these graphs. Now let us look into this. Delta G naught is equal to minus RT log Kp, where P is the partial pressure and K equilibrium constant, that is equilibrium constant based on partial pressure, and T is the temperature in Kelvin or universal gas constant, and this is called natural log. So if you want to convert this into log to the base 10, you have to multiply by 2.303. And he got another one, that is delta G naught is equal to delta H minus T delta S, where S is entropy, that is change in entropy is represented as delta S. So entropy is the degree of randomness of gaseous molecules, that is how frequently they can move here and there. So that is more associated with the gaseous molecules. Now delta G becomes negative, and this is enthalpy change. So delta G becomes a negative. When it becomes negative? When T delta S value is greater than delta H, is it not? Okay, so when T delta S is value is greater than delta H, naturally delta G will be negative. So if delta G is negative, if delta G naught is negative, then you can say this is the natural progress of the reaction or the feasibility of the reaction. Okay, so feasibility of the reaction is represented as delta G. So in that case, what about delta S? Delta S should be positive. So increase of entropy, that also indicates the feasibility of the reaction. Okay, right. Now let us check this. Let us rearrange this equation. Delta G is equal to and minus T delta S plus delta H. Let us rearrange, and once again let us rearrange this. So minus delta S into T plus delta H, that is equal to delta G, where I hope now you should be able to understand why he was able to get a straight line, because this equation represents the straight line. So that is why he got that equation, that straight line, by taking temperature in x-axis and delta G in y-axis. So when he plotted this graph, he was able to get the graph, but he was able to get the negative slope for certain cases, as I already mentioned. Okay, now let us analyze the, suppose, let us consider x is equal to, as I already mentioned, x he has taken as temperature as x and delta G as y, and C is the y-intercept, that is enthalpy change. Now the slope, you have to focus here. The slope that is represented as m here, is it not? So this slope is negative. When it becomes negative? When delta S is positive, is it not? And so that indicates the progress of the reaction. So according to D. Donder's principle of advancement of chemical reaction, it indicates, that is, minus delta G and plus delta S. They indicate the progress of the reaction, natural progress of the reaction, or you can talk about the spontaneity of the reaction. Whereas when uh, m becomes, that is, the slope becomes a positive when delta S is negative, is it not? So in that case, its negative value comes down. Are able to follow? So delta G negative value comes down. When the delta G negative value, that is negative value of the delta G comes down, that indicates that this progress of the reaction is little bit difficult. Okay, right. Now let us move further. Let us consider carbon combines with oxygen to give carbon dioxide. And let us form this 2 carbon that combines with oxygen, that gives 2 moles of carbon monoxide. Okay. Now you must note down, this acts as what? A reducing agent. That is, carbon acts as reducing agent by this reaction only. So let me explain how. Because when I see, when I say carbon as a reducing agent, it means it undergoes oxidation, is it not? A reducing agent undergoes oxidation. Okay, so thereby it acts as a reducing agent. Okay, right. Now let us see another thing. C plus O2 gives a CO2. Let us analyze the entropy change of this reaction. So we know very well that is delta S is something associated with the number of moles, that is a randomness of gaseous molecules. So it is directly proportional to the change in the number of moles of the reactant. So what about this change in number of moles, number of gaseous moles of molecules of reactant, which is nothing but sum of product of what? Number of moles of sum of number of moles of product as gases, okay, gaseous products, minus sum of, so you can put even summation symbol, okay, so sum of number of moles of gaseous reactant. So that is what is a sigma, I mean sigma or summation n reactant. Okay. Now when you look at here, after all we have got only one product, that is 1 mole. So I can put 1. And what about the gas? That is 1 mole, and this is solid. We should not take into account. So we have to consider 1 mole of reactant, 1 mole of product. Okay. Therefore 1 minus 1, that is equal to 0. So in that case, the slope is 0. So that is why it is indicated here. C combines with oxygen to give CO2. So in that case, the delta S is equal to 0. Means the slope is 0. Are able to understand? Right. And at what, it doesn't mean that the temperature is a 0. It indicates delta S alone is 0, and it is because of delta S is equal to 0, then T delta S becomes 0. But T, there should be certain temperature, probably in this case a minus 400 Kelvin. Okay, right. Uh, I think that is this 400 indicates the that is a free energy change. Okay, so as as I've already explained, the y-axis is free energy change, x-axis is the temperature. So in this case, it attains the what? That is, the slope is 0. Are you able to follow? So and that is, it means what? There is no change in free energy. Okay, right, it is in equilibrium almost. And then let us explain about the second case. Here let us consider this one. 2C plus O2 gives a 2CO. As I already mentioned, only these reactions involved in the reduction. Okay, I mean it acts as a reducing agent. Carbon acts as a reducing agent by this reaction. How? Let us calculate delta S. So 2 moles are there, and here you have 1 mole. So 2 minus 1. I have not taken into account the because it is solid. So 2 minus 1 is equal to 1. So delta S is positive. As I already mentioned, when delta S is positive, then what about the slope? It should be negative, is it not? So here delta G is equal to delta H minus a T delta S, that is positive. So delta G is negative. And not only that, in this case, that is the slope is negative. So when the slope is negative, as I already mentioned here, see this, when delta is positive and the slope is negative. I'm sorry, delta S is positive, the slope is negative. So slope is negative means it comes down like this. Are you able to see this? So delta is positive and the slope is negative. For 2C plus O2 gives a 2CO. So it comes down like this. So this is negative slope. And what about this carbon? This is a 0. Okay. Now we are talking about the positive one. Okay. Let us consider iron. So in the case of iron, that combines with oxygen to give iron oxide. So it gives 2 moles of iron oxide. Of course, this is solid, is it not? So when it is solid, now product minus a reactant. What happens here? Product is, there is no gaseous product. So minus reactant, there is 1 mole. So it means minus. So if it is a minus, it indicates only positive. So when delta S is minus, that is negative, slope is positive. Okay. So you can see almost all metals will be behaving like this only with a positive slope. It means what? That is, when I say delta S is negative, its randomness come down. Okay, so the molecules are consumed. Is it not? The gaseous molecule, that is oxygen as a gas, is combined. Its molecule randomness has come down because of the formation of metal oxide as a solid layer. Okay, and that is why when you look at the that is that graph, in most of the cases this will be of positive slope only. Are you able to understand? And even you should be able to understand one important thing, that is 2 mg. In the case of magnesium, you can find a sudden change in the slope also. It is because of the transition state, that is because of evaporation. Okay, and in certain cases there will be a melting, so that is why there is a change in the slope. Are you able to understand? So it is because of the change in the physical state after certain temperature. So one thing is clear, with the increase of temperature, the negative value of delta G comes down. It means what? Net delta G increases with the increase of temperature. So when delta G increases, what happens? Its negative value comes down. As we already mentioned, when the negative value of delta G comes down, the progress of the reaction will be little bit difficult. Are able to follow? So it cannot further move. So that is why I want to explain one important thing here. That is, so let us look at this. Now, the temperature, as I have already mentioned, this was the wonderful observation by that is this Harold, that is Ellingham. He said, let us see this. Right. So with the increase of temperature, what happens? Delta G increases. When I say delta G increases, you know very well, negative value comes down. So when negative value comes down, what do you understand from this? That is, the progress of the reaction is difficult. Now it goes on like this and attains the zero. So now you just look at it. Let me explain from the graph. See this, with the increase of temperature, 0, 200, 400, 600, 800, 1000, 1200, etc. You can observe it goes on, I mean, increasing in the overall value, but you can say decrease in the negative value. So 1200 becomes 1100 becomes 1000. Likewise, it reduces, is it not? It means what? The negative value goes down. Okay, so it means the progress of the reaction will be difficult, is it not? So it means that is at a higher temperature it is not stable. So that is the indication here. Okay, so now listen. at higher temperature. It attains a delta G becomes 0 at higher temperature. And in this critical temperature, we can classify like this. Below this high temperature where delta G is equal to 0 becomes 0, okay, where below this temperature, so below this temperature, okay, that is delta G decreases. It indicates what? There is a progress of the reaction. Above this temperature, delta G is increasing. It means metal oxide is less stable. Do you understand this? So when metal oxide is less stable, what does it indicate? That is metal decomposition takes place. Are you able to follow? So when metal decomposition takes place, it is easier to that is remove the oxygen from the metal at higher temperature. I hope now you should be able to understand why we elevate the temperature to remove the oxygen from the metal. And at the same time, we are looking for a suitable reducing agent also, okay, so that we can that is remove the oxygen at a relatively lower temperature. Now you may ask me one important question, sir, what does this red line indicates? This red line indicates, straight line indicates, that is carbon plus oxygen gives carbon monoxide. It acts as a very good reducing agent because it is more stable. Do you understand this? So when it is more stable, this can be used as a catalyst, I mean the reducing agent. So this can be used as a very good reducing agent because it can be more stable at a higher temperature. So that is why we use a carbon as the reducing agent for reducing the metal oxide. I hope everything is clear now. Okay, right. So if there is any further question, that is, you can ask me so that I'll be able to give you a better, clear answer also. So whenever you, I think that is this aspect I already explained. So what do you, when anybody asks you what is metallurgy, simply say it is a strategy to remove oxygen from metal oxide. That's all. That is metallurgy. That is the aim of metallurgy. Okay. So that can be achieved by two ways. One is by using reducing agent, is it not? So when we use the reducing agent, that is we are using the Ellingham diagram effectively. Based on that, we can appropriately select the reducing agent. Okay. So this is by the thermodynamics we are reducing, and this is the case possible in the case, I mean in the case of that is non-reactive metal oxide, so that it can be conveniently that is removed, whereas in the case of a strong reactant which has formed metal oxide, it would be very difficult to remove the oxygen even at elevated temperature. So in that case, even by using any other reducing agent, so in that case, we had to appropriately adopt a technique that is called electrochemistry. So this is the electrochemistry principle of metallurgy, and this is the thermodynamic principle of metallurgy. Okay, so whenever you are asked about the thermodynamic principle of metallurgy, you should be aware of this great Ellingham diagram. So based on this diagram, that is we are able to infer, that is what is the temperature at which we can process a particular metallurgical operations, and what is the that is reagent, I mean the reducing agent to be used. So carbon is used as a reducing agent because of its salient feature. It is more stable at higher temperature. So as we already discussed, at higher temperature, metal oxygen they decompose. So it can be easily removed. Okay, the oxygen can be easily removed at the higher temperature. In certain cases, there is a shift in the that is slope. So it is because of, in the case of mercury and even what do you call Hg also. So you can find here Hg, it is evaporating, and that is why you can see a change in the slope. And similarly, this one also, magnesium becomes a magnesium oxide. So there will be a evaporation taking place, and that is why there is a change in the slope. Okay.